Hello and welcome back to Technology Now, a weekly show from Hewlett Packard Enterprise where we take what's happening in the world and explore how it's changing the way organizations are using technology. I'm your host, Michael Bird, as Aubrey Lovell is still out of the studio this week. Now, in this episode, we are revisiting the Spaceborne Computer-2, the supercomputer at the edge of space, speeding around above our heads on the International Space Station. Wow. Now, last week, we looked at the science behind the system. This week, we're exploring how the Spaceborne Computer-2 is speeding up the time it takes for experiments to be carried out in space. The HPE Spaceborne Computer-2, or SBC-2, is the first in-space commercial edge computing and AI-enabled system to run on the International Space Station. And with that comes faster results from tests carried out by the astronauts on board. So, what experiments are being carried out? And what does having a supercomputer on board the International Space Station mean for the future of space exploration? If you're the kind of person who needs to know why, what's going on in the world, and space matters to your organization, then this podcast is for you. Oh, and if you haven't yet done so, do make sure you subscribe on your podcast app of choice so you don't miss out. Right, let's get into it. According to the Guinness Book of World Records, the International Space Station is the most expensive single thing ever built. And it's expected that its final cost will be around $150 billion. It is also the fastest manned vehicle in existence, travelling at speeds of 17,500 miles per hour or 28,000 kilometres per hour. On board, more than 3,000 experiments have taken place since its launch in 1998. That's according to NASA. But the speed it's taken to process those experiments has, until recently, been excruciatingly slow. Data collected on the ISS had to be transferred down to Earth for analysis. That's a slow process on the station's 2 megabits per second internet connection. However, that's changed with Spaceborne Computer-2, which uses edge computing aboard the ISS for the first time. That is seeing astronauts being able to use SBC-2 to carry out near real-time data processing on board and have the insights sent to Earth and analysed in minutes rather than days. So, what sorts of experiments are being carried out on board? And what difference is the speed of turnaround making to the experiments? To fill us in, I've been speaking to the man who has developed the payload software for SBC-2, Principal Investigator for Spaceborne Computer-2 at HPE, Mark Fernandez. And I started by asking him how the astronauts have reacted to having a supercomputer on the International Space Station.
The astronauts are pretty busy doing hundreds, if not thousands, of experiments for lots of folks. So they don't normally interact with Spaceborne Computer.
Really?
It is primarily the scientists and engineers on Earth that are proving to their management that, hey, my software needs to be in space. And when it gets to space, it can work correctly, and we will get our answers much faster than the way we plan to get them. That's what I'm all about, is showing the value of edge computing. We go to space to explore, and data, quote unquote, is the gold of space exploration. But I indicate that the gold is really the insight hidden in the data. And our scientists and engineers create the software to analyze the data to extract the insight.
So, Mark, we talked in the last episode about what Spaceborne Computer is. I'd love to know how it's being used and maybe some of the real impacts it's had in space, particularly, as you say, around those insights.
We have a somewhat humorous example. Was working with a government customer. NASA has a standard operating procedure that an astronaut returning from an EVA, from a spacewalk, has to examine his gloves to make sure they're not torn, stretched, bruised, etc. And to do that, it takes 2 astronauts, one of them to hold the glove in different positions under different lighting, and one to take a camera and take dozens and dozens of photographs. Then all these photographs are downloaded to Earth, and analyzed on Earth to look for tears and etc. They are not allowed to go on another spacewalk until those gloves have been examined and certified to be safe. Well, us in collaboration with NASA on Earth took all of the photographs that had ever been taken of all the EVA gloves, and we trained an artificial intelligence, an AI model, to look for tears and rips and cuts. And that took a lot of compute power here on Earth, which we have, but the result of training that model is called an inference engine, which is small. We brought that inference engine up to the International Space Station. And of course, they have their computer on ground and they have their valid test here on Earth to run their software. And as the photographs were being sent down to Earth, I grabbed a copy, processed them, annotated them. So here's a red circle and it indicates this is a possible rip. Here's a yellow circle, which indicates this is possible excessive wear and tear. And those photographs were sent down to Earth by Spaceborne. Out of 299 photographs, only 9 showed wear and tear, etc. We had to wait the 5 days until all of the photographs got back down to Earth, and they could run them through their standard procedure to come back and say, you did it, Mark. You identified the exact same thing we did here on Earth. We sent the results back down to them, and sometime later they came to us and said, well, we got good news and bad news. Good news is you matched our results bit by bit. The one that has us concerned is yours ran faster than ours did. Well, it turns out I had sent a new computer up, and their computer, being part of a government, was in its late end of its 5-year life cycle. So it was several years old, and of course I would run faster. And I was able to get those processed and down to Earth in 45 seconds. So super, super excited to go from 5 days to 45 seconds. So the value of having this capability in space is being demonstrated across numerous verticals.
So what kind of real-world impact can that have on operations in space?
I recently had the light bulb go off for me, which was shocking and disturbing that I wasn't as visionary as the people I'd been working with. So we kind of talked about the EVA gloves, and after the 5 days passed, they got back to me and said, Mark, your answer is absolutely correct, and we're super excited about that. But we want to let you know you processed 60 photographs a second. And I said, yeah, I kind of have a low-power GPU to do that, and the modern ones in gaming systems do hundreds and hundreds, and they cut me off, and they said, Dr. Fernandez, you missed the point. If you can do 60 photos a second, then you can do 60 frames of photos a second, which is video. And we want to do a secondary experiment where we don't look at photographs of the gloves after the mission. We feed you the video as the mission is going on.
Oh, wow.
And the light bulb went off. Mark, why didn't you see this coming? This is what you do. This is just awesome. So imagine the astronauts don't have to spend the time to take any photos. What if we watch them the entire 8 hours or the entire 12 hours of the mission, and we process it in near real time to let them know how their gloves are surviving the workday? That's pretty exciting.
Wow. Gosh, that's fascinating. And is there anything else that you're working on that's going to have a similar, potential impact to astronauts?
Well, DNA sequencing is one, and NASA presented some results last summer at the ISS R&D conference, in which the first ever genomic analysis from sample to insight was done in space, and it was done within 24 hours. That's 2 paradigm-changing things. And so it's a 3-part step. The first step is actually scraping up something off the wall of the space station or some mold on some of the lettuce, et cetera, and putting it into a physical DNA sequencer. And as you may know, DNA sequences are massively large. The time to get that DNA sequence back to Earth was a month. It's that large. However, only a tiny little bit of it is important, right? Well, I do that in situ. I do that in space at the edge of the edge. That insight is much smaller than the raw data, and I can get that back to the scientists much quicker. Months to minutes. We've got numerous examples of scientists have been waiting months for answers, and I can get them those answers in minutes. So I processed it in about 12 minutes and took it on to the next step and produced that report that told them what they needed to do. So that is going to be game changing. And actually in the presentation, the NASA scientist said, this is a paradigm shift. So we don't have to wait a month to find out what mold is growing on the walls or on our plants. We can have it in the morning because of Spaceborne Computer.
Mark, that was amazing. Thank you so much. And we will be back with Mark in a moment, so don't go anywhere. All right. Well, it is time for Today I Learnt, the part of the show where we take a look at something happening in the world that we think you should know about. Now, what is one of the things that separates humans from artificial intelligence? Well, it is the ability to perform a new task without prior training and relay how to do it to another human. At least that was a difference, because now a team from a university in Switzerland have recreated this uniquely human characteristic to allow an AI model to train another AI machine. The team of researchers have been able to model an artificial neural network to learn and perform a series of tasks, and then provide a linguistic description of those tasks to a sister AI. And that AI went on to perform them too. The author of the study, which was published in Nature Neuroscience, is PhD student Reader Riveland. He said the team started with an existing model of artificial neurons, which has 300 million neurons, and is pre-trained to understand language. They then connected it to another, simpler network of a few thousand neurons. In the first part of the experiment, the team trained the network to simulate the part of the brain that perceives and interprets language. The second part of the experiment trained the model to reproduce the part of the brain responsible for producing and communicating words. Alexandra Pouget, who led the research, said that as far as anyone knows, it's the first time two AI models have been able to communicate in this way. And that is particularly exciting in terms of how robots may work together in the future. Okay, well, now it's time to return to our guest, Mark Fernandez, to talk about the experiments being carried out on board the ISS using Spaceborne Computer-2. What is the ultimate goal for the Spaceborne computer? Is it for further exploration onto other planets? And if so, is there a big advantage of having a lot of processing power and a lot of storage out in some sort of remote outpost somewhere?
I don't want to sound like it's a cliche, but we need to be able to do in space what we do here on Earth. And here on Earth, not everybody gets a big computer to do their work. We share a computer. Multiple companies share cloud resources, et cetera. So the idea that you would send to space some experiments and you would bring along with you the computer to do that is cost prohibitive. However, if we could equip the next space station with a spaceborne computer, or the next lunar lander with a spaceborne computer, and we could advocate that this is available much like it's done here on Earth. What we are envisioning here at the Spaceborne Computer team is that each partner is going to have a specific thing they want to do. I want to see the DNA analysis results. I want to see the EVA glove photos. I want to see the solar flares. And when your photographs come along, we process it, send you the results, and you get them faster than you would ever before. Months become minutes, and minutes, days become seconds.
Is there a scenario where it would become the ship computer, so to speak, the computer that you can ask a question to when you're on Mars and it takes 20 minutes or 40 minutes, however long it takes to transmit a message back? Like, is there a scenario where it becomes the sort of the instruction manual?
For the present, I'm focused on the next two steps. The next first step is the moon, and the second step is Mars, and be able to help those scientists and engineers that are going there for a reason to discover and look for water, to be able to manufacture things out of lunar soil, etc. They're going to need some computing capability to figure out if that's possible and then to help them do it.
Yeah, because if you're on Mars, presumably the data transfer rates are probably going to be similar size to the data transfer rates we have on the International Space Station, but the latency is going to be pretty severe. So having compute right in front of you to be able to answer that question straight away could save lots of time and I guess resources and critical resources when you're so far away from Earth.
Yeah, absolutely. And I often jokingly use the example, if you're on Mars and you get up in the morning and you look out the window and you see a dust storm coming, you say, "Where's my weather report?" It'll be here in 40 minutes. Well, you're going to be hit by that dust storm before that occurs. So you need to be able to do your Mars dust storm weather modeling yourself. You're not going to be able to rely on that time delay.
So, Mark, what does Spaceborne Computer-2 mean to you?
Well, I have the best job there is in the world, I think, and I am head down and focused and full-time, getting all of my scientists and engineers happy and excited as they can be. They're like children on Christmas morning. I had one yesterday, and I've got a screenshot of the terminal saying, "Experiment successfully completed," and then there's 4 happy, grinning faces in that snapshot. I get to see so many light bulbs go off, and so many people get so excited when something like this works in space, which they weren't sure it was going to do in the first place, and then it works faster than they can imagine it would work, and they get their insights back home. And I get to see those light bulbs go off. It is a lifetime event.
Mark, thank you so much. It's been great to talk. And you can find more information on the topics discussed in today's episode in the show notes. Right, we are getting towards the end of the show, which means it is time for This Week in History, a look at monumental events in the world of business and technology which has changed our lives. Now, the clue last week was, it's 1960. Pew, pew, pew. Did you get it? I didn't, but I did quite enjoy making the noises. Well, anyway, it was, of course, the patenting of the laser beam, which was issued to Arthur Leonard Shawlow and Charles Hard Towns. The US patent number 2,929,922, of course, was for the optical maser, or microwave amplification by simulated emission of radiation. The theory behind the technology was originally proposed by Einstein in 1919, but it took over 3 decades before it became a practical reality. Towns had been working on maser technology since the early 1950s, but it was later in the decade when he started working with Shawlow that they developed the idea of using light instead of microwaves, and the laser, with replaced M for microwaves with L for light, was born. And along with it, an industry worth some $18 to $20 billion, according to the research firm Grand View. Incredible. Now, next week, the clue is it's 1997. So let's spin up a groundbreaking home theatre experience. Interesting. I think I know this one, and I think Aubrey probably knows this one too. So hopefully we'll see if we're right next week. Right, well, that brings us to the end of Technology Now for this week. Thank you so much to our guest, Principal Investigator for Spaceborne Computer-2 at HPE, Mark Fernandez. And to you, thank you so much for joining us. Technology Now is hosted by Aubrey Lovell and myself, Michael Bird. This episode was produced by Sam Dattapolan and Al Booth, with production support from Harry Morton, Zoe Anderson, Alicia Kempson, Alison Paisley, Alison Mitri, Camilla Patel, and Chloe Sewell. Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, Katie Guarino, and our social media designers are Alejandra Garcia, Carlos Alberto Suarez, and Ambar Maldonado. Technology Now is a Lower Street production for Hewlett Packard Enterprise, and we'll see you same time, same place next week.